Hi, welcome back to Calculus. Today we're looking at section 9.6, alternating series and what we're going to call conditional convergence. So let's start with alternating series. An alternating series is simply a series in which the terms alternate their signs. So an example of one would be the sum of negative 1 to the n times 1 over n squared. Now that negative 1 to the n in front is going to supply our alternating signs. And so most of the time when you have an alternating series, you're going to see it written with that negative 1 to a power in front because that will make the signs go back and forth. So in this case, we get the series that starts with negative 1, then adds a 4, subtracts a 9, adds a 16. One thing to really be careful of, so here I started with, I did n equals 1 to infinity. Be really careful to note where you're starting in terms of positive or negative. So since negative 1 to the first is just negative 1, I start this one with a negative and then it'll go back and forth. We'll see most of them actually are going to start with a positive. So that's an alternating series. So with alternating series, we have what's called the alternating series test, and this is going to let us know if it converges. So the sum n equals 1 to infinity of negative 1 to the n plus 1 times u sub n. Now notice here, if n is 1, 1 and 1 makes 2, so we're going to start with a positive term here. And so this would be u1 minus u2 plus u3 converges if all three of the following conditions are true. First, the individual u sub n's have to be greater than 0. Now notice the negative here is taken care of by the negative 1 to the power. So when we say that the individual u sub n's have to be bigger than 0, we're talking about this piece right here. Okay, we're not talking about the terms as we write them out. We're talking about those pieces inside the sum. 2, eventually, if you go far enough down the line, the terms start getting smaller, or at least don't get any bigger. So eventually u sub n is greater than or equal to u sub n plus 1. For a lot of these, that'll happen right away. Some of them you may have to go down a ways in the series. And finally, the third condition is that the limit as n goes to infinity of the u sub n's has to be 0. All right, so I have some examples. Let's move this computer over so you can see them better. There we go. First one is not much of an example. It certainly won't take long to talk about. Sum n equals 1 to infinity of negative 1 to the n plus 1 times 1 over 7 minus n. So right away, this fails the alternating series test because if n is bigger than 7, you start getting negative terms. And actually, if n is 7, you don't even have a term. But anyway, when n is bigger than 7, you don't have any term. Your terms are negative. And so it fails the first condition for the alternating series test that said everything had to be positive. All right, so let's look at this one. This one's a little bit more interesting. Here we have sum n equals 1 to infinity of negative 1 to the n plus 1 times 1 over n squared. Well, 1 over n squared is certainly always bigger than 0. That's guaranteed to be true, so we meet the first condition. For the second condition, the u sub n's are bigger than the u sub n plus 1. Each term is bigger than the one that comes after it, and we can just see that very quickly by listing out a few and noting, hey, the bottoms of these are always getting bigger, 1, 1/4, 1/9, 1/16, that's going to be 1/25, right? Again, no positive or negative here, we're just looking at the actual fractions. So since the denominators are getting bigger, that means that the whole term is getting smaller, so it meets criteria 2. And if you take the limit as n goes to infinity of 1 over n squared, we already know that limit, and it is 0. So this is a convergent series. Very nice. So let's get the board cleared off, and we'll do some more. All right, on this board, we're going to talk about estimating alternating sums and finding their error. So if the alternating series n equals 1 to infinity, negative 1 to the n plus 1 times u sub n satisfies the conditions for convergence. So it has to converge. If it doesn't converge, then all bets are off. Then the partial sum, s sub n equal to u sub 1 minus u sub 2 plus u sub 3 all the way out to that last one, the nth one, approximates the sum L of the series, and we can say two things. This partial sum has an error whose absolute value is less than u sub n plus 1. Its error is strictly less than the first unused term. And 2, The sum L is between any two partial sums, S sub n and S sub n plus 1. With the remainder, L minus S sub n, that has the same sign as the first unused term. So if your first unused term is positive, then the remainder between the actual sum and what you have will be positive, and if it's negative, then it'll be negative. All right, so let's look at an example. Here's this alternating series we looked at the start of the section. Sum n equals 1 to infinity, negative 1 to the n plus 1 power times 1 over n squared. So let's look at a fourth, the fourth partial sum. So the first term is 1, then minus 1/4, plus a ninth, minus 1/16. Now, if you trust me, and hopefully I did it right, but I think I did, those all add up to 115 over 144. Okay, you're welcome to check my math, but I'm pretty sure that's what it adds up to. Now, so that is our partial sum. That is our estimate for what the sum of the whole series is. And we know that the absolute value of the error has to be less than, well, my next term would be 1 over 25. So my error is just strictly less than 1 over 25. And there we go. That is estimating alternating series. All right, I've got one more board. We're going to look at something called conditional convergence. All right, the last little thing we have to look at is something called conditional convergence. So conditional convergence is just a convergence series that is not absolutely convergent. So remember, absolutely convergent means if you take the absolute value of the terms in the series, then you get a convergence, then it converges. So let's look at an example. We're going to have an example here that definitely converges, we'll show that, but that its absolute value does not. So let's look at this one. The sum n equals 1 to infinity of negative 1 to the n plus 1 times 1 over n. It converges because we can run it through the 3 points on the alternating series test. Each term is bigger than 0. Each u sub n, is bigger than 0. Remember the negatives are their own separate little piece. Certainly 1 over n is always bigger than 0. 2, u sub n is bigger than u sub n plus 1. Well, if you just start making a list, you get 1, a half, a third, a fourth. Those are definitely decreasing terms. And finally, the limit of 1 over n as n goes to infinity is 0. So it converges, but if you take its absolute value, all that does is drop out those negatives, leaving us with just the sum n equals 1 to infinity of 1 over n. But that is the harmonic series, and we already know and already saw that the harmonic series diverges. So we have conditional convergence here. The original series, the alternating series converges, the absolute value of it does not. So we don't have absolute convergence, but we do have convergence. Kind of an interesting little example. And so some really interesting things happen with conditionally convergent series. For starters, you have to actually add up their terms in order. There's a wonderful example in your book. You're welcome to look at it on page 520, where they get a series to add up to twice itself. And that doesn't make any sense. And they did that by rearranging some terms. So you cannot rearrange terms in a conditionally convergent series and get the sum to add up. You can add up finite sums and get the same thing every time. You can add up absolutely convergent series in any way you want and get them to add up the same every time, but you can't do it with a conditionally convergent series. And finally, also on page 520, you're going to find a list of just kind of bullet points for everything that we've covered so far with convergence and divergence of series. So if you're working on some problems and you're not sure which convergence test maybe that you want to be using, I would highly recommend go back to page 520 and see what's there. So there you go. That is alternating series. Yep. Have a great day.